So, so we are going to today see the impossibility of the chain structure vis-a-vis how can connect two conjugate variables. Can we have restore the causality vis-a-vis the simultaneous measurement of two observables, which is not in principle possible via uncertainty, the way we formulate uncertainty relations, that simultaneous measurement of two commutative observables, measurements of two commutative observables, it's not possible. But if we just invoke probability, if we give eigenvalue to those eigenstates, and they are probabilities of these two variables, and it's a chain, can causality be somehow causality still doesn't remain intact, and in that vis-a-vis those probabilistic measures from two states in that given chain. So this is the argumentation we are going to follow, and we are going to just see it and somehow can just arrive at that very thing. So if we have a short analysis, so if we have a sequence of values, let us have a sequence of values where we have qi, a coordinate, its measurement is mq. There's this before measurement and after measurement, it might have the same value. In the same way, another coordinate before measurement and after measurement, you can have the same value. And if they are non-commuting, this means after measurement, these variables will not necessarily have the same value in that sense. So, such that if we have a for non-commuting variables, our measurements before and after, it may not necessarily be same. That's for non-commuting. If they are simultaneous and related non-commuting variables, it's not that before and after measurement the value will come out to be same, but for non-commutative. So we can introduce a probability where probability of mq, it's qi, it's before measurement, this or you can have another. But we know from our previous thing, probability of from previous equation mu ui vk omega n. So sometimes you can in the process you can ignore, for example, in a given sequence you can ignore one of the measurables as a coordinate. So in the particular interpretation of probability, you can only take the first and the last thing into consideration. So intermediate measurements, those can be ignored. So the probabilities of measurements before and after, if we just have that very idea into consideration. So mq, qi, pk, um is equivalent to. So we can ignore one of the variables here. It will be probability of mq, qi, um. Or we can also have probability of mq, qi, mu, So this means that u doesn't depend upon m, does not depend on the value of p existing simultaneously with q. So the dependence of u on u is constructed so that one of the values of u is constructed or coordinated with the other values of possible values of u, such that you can have u is equal to f of qp. So you can have three things. Either you have an individual probability of q, individual probability of p, or probability of u and p taken together. So these are three set of probabilities. Now, in the previous thing we had once had an exercise. If we can have a measurement of simultaneous measurement of P and Q, means P and Q, P or Q, or Q or P. So if there are individual measurements of P and P or Q, is it and if you have measurements of P and Q together, can the exercise be done, and how the three measurements can relate to each other in that sense. And we can use measurements like d of p. So if we have a later construct, so here we have this idea of causal chains. So if they are causal chains, we can establish connections between d of q, d of p on the one hand, and d of u on the other hand. So if there are causal connections, so it's probability of q individual, probability of p individual. So it's du means p and q taken together. So if causality is there, we can have some connection of this can be just established. And we can also invoke something called relativistic relative probability function. So relative probability function is basically you are going to see measure one, not simultaneously taking the other two major variables or observables into consideration. You can take this, not this. You can take this, not this. So you can. This is shown. You can have this relative probability as relative probability can be denoted by d of q, p, u. Takes a causal function and establish the connection between the distributions. It can establish the connection between these distributions. Distributions of these parameters q and p, they belong to eigenstates and they have certain eigenvalues which can be connected. So relative probability corresponds to those relative distributions. That's it. Now, one further thing is, so we can say we can construct probability chains defined in such a way that we can say d of q or this idea of brackets and semicolons means q q alone, not u. Or you can have d of p, you are measuring p, one of the variables, not u alone. These can be probability distribution of q not taking u. Probability of distribution of p not taking u. So probability distribution of u is given by p and q taken together. That's it. Now we can further, in terms of, if we start from a general situation S. So we can write this general situation S can be written such that we can have d of p, q, p, and u is d of s. We can denote it by s. So it's a distribution of s relative to u. So now this is the general scheme we have set. We have taken three probabilities and we can have three measurements u, U of P, U of Q, or U, which is dependent upon U, P, and Q. And we can measure one distribution independent of the other two, or the other independent of the other two. So this is the general scheme. Now we are coming back to, if you remember, now these probability distributions are to be measured vis-a-vis the psi function, the value of psi function. It's basically a measurement of observables, but since we are interested in quantum mechanical observables, so normally you can take it as a psi function, which is the evolution of wave function. So, yeah. So you can say psi of QIQ is equivalent to, you can say in any situation we can measure an entity U, which is non-commutative for non-commutative entities. The probability of obtaining U, which is obtained by. So now, if you remember, we had described psi in terms of phi, and phi in terms of U, such that we can relate two wave functions via some U, which was an operator having indices. So an operator transformation operating such that we can relate one wave function to another, psi with phi with via sigmas. Now, if we have these two psi, which depends upon Qi and Q, so we can write it. When we wrote the measurement of those probability functions, probabilities, which correspond to those eigenstates which are being operated upon by operators and have certain eigenvalues, and those eigenvalues share that probability spread around that space. So for two conjugate observables normally would taken, so we can say they are mediated by some operator thing, sigma. So if it's an integral, so along the range of those, that integral will take the range of those eigenvalues along the probability spread. So if its psi is dependent upon this, so sigma can be written as QIU phi of UK Q du. So psi of QIQ represents measurement of Q, represents measurement of Q with result. So we can write the probability considerations. We can write the probability considerations. We can write probability considerations. Probability under consideration, probability under consideration. Such that probability of MQ, QI, MU, U will be equivalent to. So we can so it's square of probability sigma QI U square. So we are coming to the same argument, whether once we constructed the probability of square of two observables is equivalent to probability of individual squares. So once we had two interpretations of probabilities, and once we conjectured them, so for them to hold, we had to that inequality relation should be there. The relations are not exactly. So if square of probability is not equal to the individual square of the observables, so this means then once you are measuring probabilities of individual observables, it's not equivalent to the probabilities. Determination of probability for P and Q and P, Q, they will not necessarily, there's a problem. If you individually measure probabilities of two variables and see at the result, or you simultaneously measure them together, they will not come same in one of the interpretations. To have a consistency, we had that inequality relations. The same argument we are going to see here also in that sense, and we are going to see to show that its validity of that argument is again shown in that context. How we can arrive at the same thing. Such that, so if it's psi of so if it's this probability of this is equal to this probability of mq qi u will be equal to sigma of qi u square. So again, probability of dqi u. So this square and colon means you can take either this, not this taken together. It's sort of a relative probability. It's also be equivalent to sigma qi u square. So for each system of class B, we have according to rules of elimination holding probability such that dB of Q of U is integral of dB Q of P d of Q P U dP. If dB of Q of P is equivalent to dB of P is equal to dO of P. Again, we can have we can arrive at it if we have this is equal to QP, it's equal to some operator. So you can infer that dB. So dP probability of this thing is Q and not P is equal to P, or it's equal to operator operating on P. So this means D of P Q of U is equivalent to D of operator D of Q P U dP. This means distribution of QU is the same for all systems of class B, since the right hand of 14th has the same value of this. So you can see the probability distributions of P Q not U Q U. So how we can see probability distribution? Can we measure Q and relative probability of Q vis-a-vis P? So where will the probability distributions in terms of eigenvalues where they should lie? That's it. In which intervals they should lie. So again, you can say that the way we have sigma qi square, you can also have dB of Q of U will be equivalent to sigma of Q of U square. So what is now we are coming to the meaning part of it, or what does it mean that we have had distributions of these probabilities, relative distribution of these probabilities with integration along with those eigenstates, eigenvalues will lie. So what does it mean? Such that probability of SB of Q of U is dB of Q of U. So if it's 16 and it's 17, so we have to see where the contradiction is. Such that probability of S of B, Q of U is probability of M of Q, Q, M of U. So we have described this SB as the state or probability of the state of variables taken together or individually. So it's measurement of this this thing before this thing, and this is measurement of this thing before this thing. Probability of measurement of this state, which is SB, which consists of variables Q. And U is P and Q, so you should have this equivalent to this thing. So again, we are coming to. So you'll see there's a subtle the way we. So it's bit slightly needs more amount of mind involvement to exactly go through the proof of to show that once we take relative probabilities into consideration, it will also lead to some contradiction, unless and until we assume that inequality of that measurements before and after for these observables in a probability chain, we can ignore the intermediate states. So we'll see probability of S of B can be QU is equal to probability of S of B Q MU U is equal to probability of S of B MQ Q MU U is equal to probability of S of B MQ Q of U. So you see, so again, this result will lead to contradictions. Then we have the principle of elimination. Principle of elimination. If we have, if you remember, we have used principle of elimination previously also. The probability of this V1, V2, just variables A1, A2, A3, so on and An. So we can just the intermediate probabilities can be ignored. Now, if you just take this principle of elimination here, this means probability of SB U is integral of probability of SB Q, where SB is the state which we have defined, which is basic of P, Q and U is basically probability of SB Q. Can also take S as a state DQ. Probability of SB MQ U can be written as probability of SB MQ. Probability of SB MQ Q U DQ. This is measurement of Q. This is U. You can see it like this. So we have, this is measurement of this. You can see it this thing. So we can use our previous probability of measurement of state. This SBU is equal to probability of SB MQU, and probability of SB MU U is equal to probability of SB measurement of MU. So this thing will contradict the inequality. So if we replace mu by ui, if we replaced mu by ui, mu by ui, and from this you can at the end, if you just have not so it needs more amount of mental effort to just work it out, the proof. So if you are not convinced by this, you can just take some more time. The argument is basically that the probability of distributions of Q and P should not be equivalent to D of P. So if you have measured this probability distribution, relative probability of Q, and taken, you did not concentrate on P, but you had taken them together. You can measure Q, but P is simultaneously variable as it together. It's not as if you are going to measure individual project probability. So, so even though you have measured Q, but there is a relative measurement of Q vis-a-vis P. But the thing is, you have measured Q only. But it's not the same thing as if you are measuring P taken individually. So what it has to say is something about causality or probability chain. So the important point which I would like to emphasize, or which this book tries to emphasize, is that uh, uh, is that so although in this case P in this case are dependent on Qi, one might argue that this is not to be regarded as a kind of causal dependency. So you can say from this, you can say that from this you can argue indirectly that Q and P are somehow related. But the argument made here is that it should not be regarded as some sort of causal dependence. Dependence. Because sometimes when we consider the simultaneous measurement of two variables, in that case, the unobserved thing should be related with something which is to be observed and whose measurement is to be taken into account. So P and Q can be taken. P and Q can be taken as independent parameters of physical occurrences, in the sense that P and Q they are arbitrarily they can be arbitrarily chosen. And causal dependence in the sense when U can be seen vis-a-vis P and Q. They are related. If they are related in some, when we try to have measurements in some simultaneous sense, if we take them as in the non-commutative sense, you can say that. If we are trying to intend to have measurements in that so in that sense, from this you can argue that our measurements, probability measurements of this thing, D of Q and D of PQ, they can be taken as separate measurement of these variables, whether conjugate or otherwise. So they are individual, whatever probability distributions, or they have separate values independent of probability values independent of each other. You can see it that way. And from this, one of the important things which we can see that right is that that the chosen values could never be invalid, be shown to be invalid. So the question is that the chosen values can never shown to be invalid if we assume that that every observation, or rather every measurement observes or disturbs things in unknown ways. We cannot quantify things. So it will be terribly vague, or it will be lead to even the indeterminacy. We can somehow quantify it for simultaneous things. But from these probability arguments, if they are not somehow, we cannot show them in a causal chain, whether once we say that a relative measurement of probabilities of an individual probability is not equivalent to when we measure it individually separately. So it leads to an argumentation whether so we have P and Q have causal dependence, some sort of causal dependence, or they can be here. The question is can whether P and Q are causally dependent, or we have to take them independently. And further, we can just from this argue that P, Q, and these are their measurement of these probabilities are not dependent on each other. And from this, if you want to measure things, these chosen values could never be, you have not to see them. If you assume that we can observe or measure things in unknown ways, how can we quantify the indeterminacy relation? That will be problem. Because if you assume that the disturbance by observation, so if you take that argument, then the disturbance by observation will depend upon these probability arguments, or other mathematical or so an interpretation of it will be contingent upon the logic of probabilities. That's in that sense. So the whole crux of the argument is that we have arrived at we cannot show this causality cannot even be restored for two variables taken separately or taken together from the chain structure. We cannot just restore it even from that thing also. Leave away the way we have articulated indeterminacy principles or uncertainty relations in terms of simultaneous measurement of two commuting observable or measurements. They can be non-commutative, or they cannot be measured in a simultaneous sense. So we have come to the same thing, but via the integrate web of probability arguments. How we can see the chain structure How we can relate eigenstates and eigenvalues, which are basically probability distributions of two variables. They can be in some located in some space. So that's it. So we continue.